Okay, a pleasant morning and afternoon to all of you. I hope you are doing great and awesome. For today's lesson, we will go right away to our main focus for this session. So our session will be about the unit 1, function transformation. I believe most of you have already encountered a transformation. Look at your face in the past and compare it to your face now in the present, then there is always a transformation. Same with the function. Okay, so to continue, we also, or to highlight with the topic about function transformation, we will just focus on the horizontal and vertical translation. So I hope we are doing good and great in the midst of pandemic. We are still on fire in our online classes. I believe you are. I hope so, or I am just assuming. Okay, so I guess you are ready. So let's continue. So it's very important to be guided with our learning objectives for today's lesson. So here are the things that I want you to focus on. So we will determine the effects of h and k in y minus k equals f of x minus h. So I want everyone to highlight, or what I mean, remember the form for this function y minus k equals f of x minus h, because later we will be we will be talking about it more. Oh, I'm lost. Okay, this is what I want you to focus on later, or try to remember, because later we will talk more of that form. And of course, the main thing in here, so the y equals f of x. So I hope we are very clear about it. So next, so to continue, oh, I'm lost. Okay, so it has a lot of advertisement. Okay, so next is sketching the graph of y minus k equals f of x minus h for given values of h and k, given the graph of y equals f of x. So I hope we are clear about it. And of course, the last objectives that we're going to learn this in this session is about writing the equation of a function whose graph is vertical and or horizontal translation of the graph of y equals f of x. So are you ready? I guess you're all ready. Let's get it on. Okay. So now I want to highlight these key terms, or enhancing your vocabularies, because later on you will encounter these, and I want you to remember the terms after in this discussion or session. Okay, so to continue, of course, we have the transformation, as I mentioned a while ago. We also have the mapping, and we also have the translation and image point. These are the terms that you are going to encounter in this and in the next slide that we have in this session. So now let's start this one with a trivia, perhaps. So did you know that Albert Einstein is often regarded as the father of modern physics? He won the Nobel Prize for Physics in 1921 for his services, or what I mean, he won the Nobel Prize for Physics in 1921 for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. And this photoelectric effect is the Lorentz, or it uses the concept of Lorentz transformation, which is very important part, or it plays an important part of Einstein's theory of relativity. So meaning, if you want, if you really want to explore and study the theory of relativity of Einstein, so better you have to master this concept of transformation that we have in this session. Okay, who wants to be like Einstein? I want to be like Einstein. Okay, so every one of us really wanted to have, wants to really develop your critical thinking skills, and of course your content based skill. What I mean, the content itself in mathematics. Okay, so now, okay, so now I'm just, okay, I'll just turn on the pen so that later it will be easier for us to handle this. Okay, so let's do the think, pair, share activity, and then perhaps you can do it in your as you watch this video, and we will just continue later about the activity. So find a situation where there is geometric transformation. If you can show some photos, you may show it to your teacher. But let's try to think about, or let's try to pause for a moment and try to think about a situation where you can apply the geometric transformation. I want you to be, since we are in the online class, I know you are inside in your houses, so I want you to observe in your surroundings, in your room or in your house, and try to figure out if there is something geometric transformation is happening, or what I mean happening rather, in your place. Do you think you have? You can share it later to me, okay, after in this discussion. Okay, think 1 minute and raise your hand if you want to share. I guess later in our activity, I will be asking someone to share it. Or if you want to share, then just tell me. Okay, I'll give you the chance to share it. So these are the examples, I guess. So very nice picture, right? It shows transformation. It's like reflection, correct? There is a reflection in it, and it shows transformation. Another picture that shows geometric transformations. We have it. The zebra, who loves zebra here, who looks like a zebra. I guess no one. Okay, next, of course, to the pictures that we have there on the screen, it shows, or it is related to the word transformations, or shall I say, there is a transformation in the pictures that I've shown. Okay, so let's try to define it formally. When we say transformation in geometry, as you can see, a transformation also means to change. So there is a change in position, change in location. Okay, so there is a change in transformation. And when a figure moves from one place to another on a coordinate plane, a transformation has occurred. So I want you to remember about it. Okay, think about it. And now here's the basic principle or common thing that we have to remember, or yeah, we need to remember about a transformation. The original figure has changed positions. So this is the main concept of a transformation. As you can see in the picture or this image, we have original image and it turns into a new image, or it moves into another image. So there is a change of image, in short, the position itself. So that is the basic concept of transformation when we are in geometry. Now let's try to compare about this one when we are in function or in pre-calculus. How do we relate transformation in pre-calculus? So I hope we are still alive there. Yes, I know you are. I hope so. Yeah. So now I'll just erase this one first. Okay. No. Okay. So let's proceed. Now, these are the guide questions. I want you to be guided, of course, in this topic. How do we describe a transformation of function? So I want you to think about this one, about how do we describe how do we describe a transformation of function. So next, what is the importance of mapping in transformation of function? So let's discover this one later. How do we describe the notation for mapping? So there is a notation for mapping that we have to remember here. And how do we define translation? So we use the word translation later. We will discuss it. And of course, how to illustrate a translation of function. And lastly, how do we describe and illustrate a horizontal and vertical translation? I hope we will be able to answer these questions later as we go, as we start. So let's get started. Okay, let's start. Of course, let's start about this one, a linear frieze. Are you familiar with the linear frieze term? In this topic, I've just heard it here. Okay, in this book that I'm using, or we are using rather. So let's start with this. A linear frieze, rather, is a pattern. Of course, is a decorative pattern in which section of the pattern repeats. So I highlight the word repeats along a straight line. These patterns often occur in border decorations and textiles. So frieze patterns are also rather used by artists, craftspeople, musicians, choreographers, And mathematicians, of course. Can you think of places where you have seen a freeze pattern? So the good thing is, I have an example here. So this is an example of a freeze pattern. As you can see, there are repetitions of patterns, okay? The pattern repeats itself along a straight line, as you can see, right? Look at the picture. So nice to go here, right? So this is an example of a lantern festival in China. So this is an example of a freeze pattern. So I hope you are guided about this one. And let's proceed. Now, let's try to define what is a freeze pattern and how does it relate to our topic for this session. A freeze pattern is a strip design that repeats itself, as I mentioned. So examples, we have the decorative borders, tracks made by tie threads, ancient Greek urns. So this one, ancient Greek urns, is this the one? I guess so. And now, okay, when we talk about a freeze pattern, it can be also described as as patterns rather that repeat in a straight a straight vertical or horizontal line. So that can be found in architecture, fabrics, and wallpapers. And I believe this is something to do with our topic for this session. So how does it relate to our topic? Okay, we use the term patterns. We use the term repeat or repeating patterns horizontally and vertically. So something related to a transformation. So let's try to investigate this by pair. Of course, I want you to do it later perhaps. So let's just run through on this. Okay, investigate vertical and horizontal translation. So you have the graph y equals f of x. This is our base function or base function or first equation that we have or first function that we have. And this is the graph or the next function or form of function that we have y minus k equals f of x. So let's try to compare the graphs of this parent function or the base function into the transform function y minus k equals f of x. Oh, I mentioned the word transform function. Yes, exactly. This is an example of a transform function, a function rather. I will tell you later about it. Okay, so the first one is consider the function f of x equals the absolute value of x. So this is our base function. Sorry, I have to clean it up first before we'll continue. So I hope we can follow. So consider the function, this one. Okay, so again, we don't be lost in the middle of the discussion. This is our main goal here to investigate the vertical and horizontal translations. So you have it there, use the table of values. So you're familiar about the table of values in graph, right? Again, do not forget, this is our function. So compare the output values for y equals f of x. So, and also to the function y equals f of x plus 3. And of course, y equals f of x minus 3. So these are same with this pattern, right? Can you follow? And this one is same with this pattern. So let's try to compare their graphs later. Okay, so I know you're all excited. You can do it while I am talking in here. So we have to input the values in here in the given output that we have or functions, the three functions that we have, f of x plus 3, and f of x minus 3. Okay, so you have here the input values. We'll use -3, -2, -1, and 0. And of course, 1, 2, and 3. So now we are going to graph the functions on the same set of coordinate axes. Okay, I'm so excited that I want you to be involved with this. Okay, so describe how the graphs of y equals f of x plus 3 and y is equal to f of x minus 3 compared to the graph of the base function y equals f of x. So relative to the graph of y equals f of x, what information about the graph of y equals f of x plus k does k provide? So I want you to try to locate about your k here in this form rather. Okay? So I want you to identify your k and try to describe the behavior of it. How will it affect the graph or the table of values or the whole function itself? So would the relationship between the graph of y equals f of x and this one and also has changed, or if f of x is equal to x or f of x is equal to x squared, then explain. So later, After in this video discussion or recorded video discussion, I'll be asking someone about this one in this activity. And of course, if you have some questions, you can just raise it later yet. Okay, so you have to do that one. And now let us check and study and compare what have you about the outcome that you have. Okay, what you have rather there. So now to start in number one, we are going to input the values. In short, provide the table of values for your x. Given values here, as you can see. Okay, this is the value. And of course, your f of x. So your f of x is this one. So this one is based on the parent function. Let's say parent function, that is the base function. Okay, take down note of that. Parent function, the base function, the basis of everything that never, that is our origin rather. Okay, base function or parent function. So f of x is equal to the absolute value of x. We use this one to fill in this table. So we have to fill it out rather the table. So you have it from -3. Since x is -3, it becomes +3. -2 becomes +2, again, based on this given function. So we have it 1, 0 until we have it 3. And after that, we will input the table for y equals f of x is +3 from this third column of our table of values. So you have it from 3 plus 3, then you got 6. 2 plus 3, you got 5. Down to 3 plus 3, you got 6. So that's how you arrive in here, or you got the values in here in the third column. And of course, for the fourth column, we will just, this one, in the given based on the problem. For example, that we have for investigation part, this one for f of x minus 3, we will just subtract -3 to your f of x. Oh, so the solution, or it seems that the board is so messy, I have to clean it up. Okay, so this one, subtract it following this, so it gives you 0. 3 minus 3 is 0, then 2 minus 3, that gives you -1. 1 minus 3 will give you -2, so on and so forth until you come up with 0. Okay, so after we have, or after we fill in the table of values that we need to, then it's very easy for us to, to graph the function. So the graph is this. Okay, so I have a messy PowerPoint presentation, so sorry. Maybe I can improve next time around. Okay, as you can see, the graph of base function, of course, this one. So you're familiar with the base function, which is given in letter A. Okay, number 1. And as you can see, for the second, or this one, for the y equals f of x plus 3. So this is its graph. So again, we change the f of x into the absolute value of x because our f of x based on the given is the absolute value of x. Okay, so I hope you will not be confused about it. And of course, this one, y equals the absolute value of -3, absolute value of x rather -3. This is taken from this. So I hope you are guided. So now I have to erase this one so that you can observe the difference. Okay, I know you're all ready to describe it. So what can you say about the graph? Okay, from the base function, it moves up. How many? Okay, 3 units from 1, 2, 3. So it moves 3 units up in here to have it the absolute value of x plus 3. And for the absolute value of x minus 3, it moves downward. How many times? 3 times. Yes, exactly. So that's your observation perhaps. So now let's try to relate this and discuss this one for our topic actually. Okay, for number 2 first, describe how the graphs of y equals f of x plus 3 and y equals f of x minus 3 compared to the graph of y equals f of x. So the answer is the graphs are translated vertically by +3 and -3 respectively, as I have shown a while ago. And of course, relative to the graph of y equals f of x, what information about the graph of y equals f of x plus k does k provide? Okay, so easy. The variable k indicates the height of the translated graph in the relation to the original function. So as you can notice a while ago, the graph moves up or down. So that's the indicator, or that's the job of K. It indicates the height of the translated function. Okay, so I hope we're clear about it. Okay, now let's check and study still with the relationship between the graphs of y equals f of x and y equals f of x plus k change if f of x or equals x, or f of x is equal to x squared. Explain. No, of course, the k variable affects the vertical translation of the graph regardless of the value of f of x. So in short, I just want to highlight this one. It will never change at all. They are always congruent, even if you translated or even if you transform the parent function to another into a new image or new function. Okay, so please take note of that, that whether you transform parent function or base function to another image or another function, it will still be congruent. Okay, so do not forget that one very important concept. Okay, now let's try to link all the ideas that we have in the activity. So we can say that a transformation of a function alters the equation in any combination of the location, shape, and orientation of the graph. Another thing also that we need to remember in here, points on the original graph correspond to points on the transformed or image or graph. In short, the relationship between the relationship between these sets of points, I'm talking about the points on the original graph, correspond to the points on the transformed or image or graph. So this relationship or set, or the relationship between these sets of points, can be called, or can be represented, or can be called as mapping. So now, yes, mapping notation can be used to show a relationship between the coordinates of a set of points x, y, and the coordinates of the corresponding set of points x and y plus 3. For example, as xy is mapped to x and y plus 3. So we took this one again. You remember a while ago, we took this one from the given in the previous activity that we have, the positive 3 and negative 3, the movements up and down. So we got this one as an example. Okay, now, did you know, this one was taken from x and y plus k. Okay, I want you to remember this one. This is a mapping notation, an example of a mapping notation form. So did you know, did you know, I'm always saying it, did you know that transformation is a change made to a figure or a relationship such that the figure or the graph of the relation is shifted or changed in shape? Okay, so I want you to remember the definition of a transformation. As long as it moves, it has changed its image or shape, or even if it does not change, then as long as it has changed its position, then that's considered as transformation. Okay, when you try to, the concept in it is like this. The graph that we had encountered in our previous years, or courses or subjects in mathematics, it's already moving. Okay, it's moving, and that's the essence or the concept of transformation. It's moving, it's shifting. Okay, so another thing also for mapping, the relating of one set of points to another set of points, so that each point in the original set corresponds to exactly one point in the image set. And of course, another thing, mapping notation is an alternate notation for function notation. For example, we have f of x is equal to 3x plus 4. This one, I'll highlight this one. It can be written as this form. So this is an example of a mapping notation. Okay, so from the function that we have, we can represent it in this form. So this can be read as f is a function that maps x to 3x plus 4. Okay, so I'll just have to erase the writings because it's so messy. So this one can be read as, again, f is a function that maps x to 3x plus 4. So I hope we'll be able to read it. Okay, so I hope we are all okay. Are we all good? So yes, you are good, and you don't have a choice to be really to feel good, or else you'll not survive in this lesson. So what is translation of function again? Okay, when we say translation of function, oh, you're wondering, why? What's the difference between transformation or translation? A translation is a subset or a part of a transformation. In short, the movements of your graph in a Cartesian coordinate plane, that is a transformation. It is categorized into three types of movements or shifts or transformations, shall I say. You have translation, you have reflection, and you have stretches. So please take down note of that. Translation is a part of transformation, but there is something identity or definition of it that we have to remember. When we say translation, as you can see, okay, a translation is a type of transformation, or it is a part of transformation. It can move the graph of a function up, down, left, or right. A translation occurs when the location rather of a graph changes, but not its shape or orientation. So what does it mean? So if you have something like movement or transformation, a type of transformation when the graph moves from left to right or up or down, then that refers to translation. And in a translation class, okay, I'm so fast. And in a translation, it moves or it changes its location, but never its shape and orientation. When we say orientation, it's ordered pairs. Okay, the key points. Okay, so in short, it changes its position or location, but it never changes the whole shape or its shape or orientation. I want to highlight that one. So please take note of that. Okay, so yes, that's it. So next, a translation is a slide transformation that results in a shift of a graph without changing its shape or orientation. So I want you to remember that one. And let's continue. A vertical, there are two types of translation that we have to consider. We have vertical and horizontal translation. Translations rather are types of transformation with equations of the form of y minus k equals f of x and y equals f of x minus h. So as you can see, this one for horizontal and this is for vertical translation. So I want you to remember this one, the two forms of, of a function for both vertical and horizontal. So again, this is for horizontal. No, for vertical, sorry. I made the wrong arrow. Okay, this one for the vertical and this one is for the horizontal. So I want you to remember the form and the function form for vertical and horizontal translation. So a translated graph is congruent to the original graph. So I want to highlight this one. Okay, so this is what I said a while ago. Please remember that the translated function is congruent to its base or parent function. That means even if it is translating or moving from one place to another, the graph, it will always be congruent to the transformed graph. The original function is always, or the parent function is always congruent to the transformed or translated graph. So I hope we are clear about it. And of course, let's have an example. So here we are going to graph the functions. As you can see, oh, sorry, the function y equals x squared, the parent function, and also this function, and also this function. So describe how they are graphs and then compare it to y equals x squared, which is our original function. So I hope you can follow. Now the solution, let the notation y minus k, this one, remember, for vertical, right, is often used instead of y is equal to f of x plus k. So I guess this is better than this form. Okay, so it's up to you which one that you are very comfortable to use. So to emphasize that this is a transformation in y, so in this case the base function is f of x equals x squared, so as I mentioned, and you have to identify your k. Your k is 2. Why 2? Of course, if you're going to have it like this, rewrite it, you can have it x squared, sorry. Oh, sorry, I don't know how to write using my laptop. Okay, this one. You can rewrite it as y equals x squared plus 2. Therefore, your k is 2. Okay, so I hope we are clear about this one. Okay, so now the notation y equals f of x minus h shows that this is a transformation on x. Wow. So meaning to say, in this case, the base function f of x is equal to x squared and the value of h is 5. So taken from this, so I hope we can follow. I have to clear up the mess. Okay, this one. So as I have said, we got h is equal to 5 from this function. So I hope we are guided. Okay, so now rearrange equations as needed and use table of values to help you graph the functions. So now we have it here, the table of values. So this is the base function that we have. Okay, it's up to you. Which one do you think, or what values of your x that you're going to use? So I use this value, so we just fill it out. Okay, fill in the blanks rather. Fill in the table. Fill in the table. Okay, so now continue for after that one. After getting this part, you may just copy your x and then just add 2 just to satisfy the second function that we have. Okay, so you have 11 until 11 here. And then of course, this is for the y minus k equals f of x. And of course, the third table represents this function. Okay, the third one. So I hope we are clear about this one. Okay, are we all right? Yes, I know we're all right. Okay, so we got this one from again. We what? So from x that you have 2, 3, 4, 5. Oh, where did we get 2, 3, 4, 3, 2, 3, 4, 5, 6? Where did we get it? Okay, to get the 9. So from, we got this one from y is equal to f of x minus h. Okay, so I hope we are clear on this. Okay, so from here, then we can now graph the function, or from the table of values that we have. We will graph it here. So this is the graph. You can do it by yourself using your graphing paper. And of course, as you can see, for y equals x squared plus 2, the input values are the same, but the output values change. As you can see, in x squared plus 2. Okay, so the input values, this one, they're just the same compared to the base function, right? But they have changed their output values. I'm referring to the value of your y. So it becomes 11, 6, 3, 2, 3, 6, 11 compared to this, right? So I hope we can follow. Oh, it's so messy. This is what I mean. They are different. Okay, they are different now. So this is what we call the input values are the same, -3. Look at their x values. And of course, the the output values has changed. So each point xy on the graph of y equals x squared can be transformed or can be represented by a mapping notation x and y plus 2. So as you can see, we add 2 in here since our k is 2. Okay, so I hope we are clear about this one. So once again, we have y plus 2 because your k is 2 based on the given. So next, the graph moves 2 units up since k is equal to 2. So from here, you move it 2 units up. Okay, so I hope we can follow. And of course, for this y equals x minus 5 quantity squared, to maintain the same output values as the base function table, the input values are different. Every point xy on the graph of y equals x squared is transformed to x plus 5y. So as you can see here, it's very pretty obvious. Since your h is 5, your x is added with 5. So if that means, sorry, I have to highlight this one. It seems that, okay, this one. Okay, x plus 5. We add 5 because our h is 5 based on the given function. So that means, as you can see also, the same output values as as the base function table. So look at, they have the same output, right? Correct? But they have different x compared to the parent function. Why is that so? Because of the function that we have. We just substituted it from x. Okay? Look at their x. It's different compared to this. Okay? Look at. But they have the same y. So this is the meaning of this. That to maintain, or in this function, to maintain the same output values as the base function table, the input values are different. And every point on the graph of y equals x squared is transformed to x plus 5 and y, which can be represented in this mapping. So how do the input changes relate to the translation direction? So your h, look at the movement of your h. I want you to try to be observant in here. Look at. So from here, from the base function that we have, it moves how many? Okay, 1, 2, 3, 4, 5 units. What I saw, sorry. Yeah, 5 units. The graph moves 5 units to the right. It's not 2, it's 5. So sorry. 5 units to the right because your h is 5. So that's it. That's the meaning of that. So in short, your k determines the movement or the translation of your graph from up or down. That is the job of your k. And for your h, that will indicate the movement or the shift of your graph from left to right. Take down note of that. Okay, so I hope we're clear about this one. Now, let's try to answer the second example. Describe how the graphs of y minus 2 equals x squared and y equals quantity x minus 5 close quantity squared compared to the graph of the base function, or you call it parent function. So the transformed graphs are congruent to the graph of y equals x squared. So they're always congruent. Even if you translate them several times, it will always be this congruent, or they are always be the same. Okay, why? Because you took that one from the base function. It's like a parent has a son. Where did has a son or a child? Where does the child came from? Of course, from the parents. So they're just the same thing, same blood, same genes. Okay, so it's just like that. So now, oh sorry, each point xy on the graph of y equals x squared is transformed to become the point x, and then y plus 2 on the graph y minus 2 equals x squared using mapping notation. So xy, so we have it x and then y plus 2. This is from this, right? From your k. If you could still remember, we took this one from y plus k based on the example that we have in the previous slides. Therefore, the graph of y minus 2 equals x squared is the graph of y equals x squared translated vertically to 2 units up. Okay, another thing also, each point xy on the graph of y equals x squared is also transformed to become x plus 5y, which shows in this mapping notation. So with that, this describes the movement of the graph horizontally 5 units to the right. Okay, so always remember in the horizontal and vertical translations, remember its form. This is a form for the horizontal translation, and this is the form for the vertical translations. And please identify your h and your k for the translations. So if it is h, that means it moves either to the left or to the right or horizontally. And if it is k, that describes the movements of your y-axis, which is the up or down. So that's it, as simple as that. Okay, so let's now proceed. Okay, of course, the key ideas in here. Translations are transformations that shift all points on the graph of a function up, down, left, and right, as I mentioned a while ago, without changing the shape or orientation of the graph. So as you can see, you have two forms in here. This one, remember this form? This is for the vertical translation, and this one is a form for horizontal translation. Okay, so I hope we are clear. Sorry, This one, this one is both. These two forms are both vertical translation. Again, this is a vertical translation. So it shows that the vertical translation, so if k is greater than 0, then it moves up. If k is less than 0, it moves down. Simple as that. So this is its mapping notation form. So this is an example. As you can see, it moves up and it moves down. So showing moving up, moving in the y-axis for vertical translation. And of course, for the horizontal translation, remember the form y equals f of x minus h. Find your h. Of course, your h shows the horizontal translation. And if h is greater than 0, then it goes to the right. And if h is less than 0, then it goes to the left. And it can be represented by a mapping notation where you add h plus h to your x coordinates. And as you can see on the graph, it's moving from left to right, or it moves in the along the x-axis, and that is a translation. Okay, so I guess we call it a day. So you have a quiz. I want you to answer that one later, perhaps after in our discussion. So if you have some questions, feel free to ask me. That's all for transformations. Again, we are just we are just in part one of transformation, the vertical and horizontal translations. Always remember that math will not make you will not make your brain complicated, but it will make the complicated things simple. Okay, so have a great day, everyone. That's all.